All right, guys, today we're doing problem 2038. Remove colored pieces if both neighbors are the same color. That is quite an extensive title. I thought this problem would be a good Leetcode candidate because it kind of follows this interesting like uh, like like flow of thinking, right? Where this is a problem where it seems like it's simple, and then upon further consideration, you start to wonder if there's something that can make it actually very complicated. But then you realize that, well, that complicated scenario that you're considering couldn't occur, and then it becomes pretty straightforward and simple again, right? So it's simple. You think about it, you go, oh wait, maybe this is actually complicated. Oh, never mind, that can't happen. It's actually simple. All right. So with that in mind, let's go ahead and get right into the problem. Okay. So you're given n pieces arranged in a line. All right. And each piece is either colored A or B. All right. You're given a string colors of length n where colors of I is the color of the ith piece. All right. So you're given this colors of I, colors array, excuse me, and each element is either A or B. Okay. And I'm just going to randomly start populating this with different values to give you an example, right? And did it say it's of length n? Yep, and it's of length n. All right, so this thing has length n. All right, pretty straightforward. Now, there's two characters, Alice and Bob, and they're playing a game where they take alternating turns. All right, this is like a super common problem statement in Leetcode, right? There's a game. There's Alice. There's Bob. They're doing things alternating. Who's gonna win, right? This structure is super common within Leetcode problems or any problem, right? Maybe if you were in an interview, they wouldn't call them Alice and Bob. They call them, Jim and Pam or whatever. But ultimately, right, this is a pretty common problem statement. And usually these problems also have what, if you're familiar with this, at the end it says who's gonna win and assume they both play optimally. Assume Alice and Bob play optimally. Return who wins, true or false, depending on who wins. Right. So this problem flow, right, this style, this pattern is super common within Leetcode. But anyways, so Alice and Bob are playing a game where they take alternating turns removing pieces from the line. In this game, Alice moves first. Okay. So Alice is going to go first. So let's just make some notes of things that are important in this description. All right. So Alice goes first. All right. Alice goes first. Now, here are the rules. Alice is only allowed to remove a piece colored A, okay? Alice removes A's. All right, so Alice can't touch B's, all right? And she can only remove a piece colored A if both of its neighbors are also colored A. Okay, so what that basically means, right, is that both neighbors are A, right? So can only remove an A if it's like this. She can remove this A right here. Hopefully that makes sense. And within this example, right, we could look at each thing. We say, could Alice remove this A? Well, are both of its neighbors A? No, one neighbor is nothing and one neighbor is B, so it can't be removed. Can Alice remove this B? No, she can't remove B's because she can only remove A's. Can she remove this other B? No. This other B? No. Can she remove this A? Well, one neighbor is A, but both neighbors need to be A, so no, she can't remove this A. Can she remove this A? Well, yes, because one neighbor is A, the other neighbor is A, and it's an A, so yes, she could remove that A. Could she remove this A? Yes, she could, because there's one neighbor A, another neighbor A, so yes, she can remove this A. Could she remove this A? Well, one neighbor is A, the other neighbor is B, so no. And then finally, can she remove the B? No, she can't remove the B. So those are the things that Alice could remove, I guess. Now, and she's not allowed to remove pieces that are color B. Okay, yeah, because she's removing A's. All right, so Alice removes A's, so I'm guessing Bob removes B's, right? So Bob is allowed to remove a piece colored B if both of its neighbors are also colored B. So it's the same exact game, but instead it's for Bob, right? So could Bob is the same, but he's for B's. Bob's for B's. Bob, same rules, but for B's. And that, I just didn't write everything out, being lazy, and now maybe the instructions aren't clear, but whatever. So let's just go through what Bob can do, right? So can Bob remove this A, this first A, right? This first A here? No, because, well, Bob can only remove B's. Can Bob remove this B? No, because the neighbor is A and both neighbors need to be B's. Can Bob remove this B? Well, the left neighbor is B, the right neighbor is B, so yes, remove this B. And I know I'm kind of exhausting this idea, but I just kind of want to make it super clear. All right. Can Bob remove this B? No, because both neighbors need to be B. Can't remove A's. Can remove this B? No. Now, one kind of weird thing to notice is you can't remove, yeah, see this rule right here, you can't remove pieces from the side, the edges of the line, because there's no neighbor, right? Because both neighbors need to be A to remove this A. Well, there is no neighbor to the side, right? So even if this was, for example, A like that, right? You might say, oh, look, both its neighbors are A and nothing. No, both neighbors need to be A. So that's just something to consider. All right. If a player cannot make a move on their turn, that means the player loses and the other player wins. All right, so whoever has no move loses, right? So this is definitely a game where, depending on the game, going first can be advantageous, right? Like chess, for example, right? It's a huge advantage to go first. But in other games, like this one, for example, it's actually advantageous to go second. Why? Because the first person who goes is going to remove something, and then the next person is going to remove something. So the first person is always like one ahead of you, right? Like if you both only have one move, the second person is going to win because the first person is going to go, and then the second person is going to go, and then the first person is going to have nothing left, right? For example, in this example here, right? Let's change this up a little bit so that it's an example where we have just 1 and 1. All right, so in this example, B has one removal and A has one removal, right? So Alice goes first, and Alice is going to remove this A, right? So then the new array becomes A, B, 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 A. I'm removing this A, B. And then Bob's going to do what? Bob's going to remove this B. So then the new array becomes A, B, B. I removed one of the A's and one of the B's. Apologies. And then, well, now Alice is in trouble. Alice has no move, right? Because this game is advantageous to Bob because he goes second. Even though they both have one move, right? Alice loses when they have the same number of moves. And Alice definitely loses if she has less moves than Bob, right? So what I'm trying to do that is say, whatever the number of valid moves are is what we'll figure out in a second, and where there might be something complicated, but we realize there isn't really anything complicated, right? But let's call the magnitude of A the number of moves that Alice can make, right? Now, this might change, right? Because you could think about the fact that, like, when Bob removes a piece, all the pieces kind of shift in, right? Like here, right? When Bob removes this piece, when Alice removes this piece, let's start there, these pieces get shifted in, right? So is that going to change the number of moves that we can make, right? Like, if I remove a piece and then I push two pieces together, well, maybe now Bob has a neighbor, another Bob, where before he didn't. You see what I'm saying? So but let's just say generally A is the number of moves that Alice can make in total, okay? But maybe that changes or whatever. And this is the number of moves that Bob can make. Well, since Alice goes first, we saw in this example when they both only had one move, Bob won because he went second, right? Because Alice removed one, Bob removed one, now it's on Alice again. So Alice can only win if she's strictly greater than Bob, right? The number of moves that Alice can do is strictly greater than the number of moves that Bob can do, then Alice wins. Why? Because if they both make, if she has 3 moves and he has 3 moves, well, she'll do a move, then he'll do a move, then she'll do a move, and he'll do a move, and she'll do a move, and he'll do a move, and then she has 0, and there's 0 and 0, but she's the first one to encounter 0. Right? So in order for Alice to win, she has to have strictly greater than Bob. If she has less than Bob, well, then of course she's going to lose, right? I mean, I don't know if I really need to explain that, right? If there's 2 moves for Alice and 3 moves for Bob, well, she's going to move and she's going to have 1 left. He's going to have 2 left. She's going to move. She's going to have 0 left. He's going to have 1 left. She's going to move and she can't move because she's at 0. She loses. Right? So strictly greater in order for Alice to win. I hope that makes sense. But now what we need to do is figure out what these values are, right? We know it's true that Alice wins when The moves that she can make is strictly greater than the number of moves that Bob can make. All right, well, that seems pretty intuitive. But how do we know what these number of moves are? Okay. Well, the easiest way, right, would be to literally just go through the array, right? And then let's see these examples here. These examples are all kind of bad, unfortunately. This is 1, 2, 3, 4, 5, 6, 7 B's, 7 B's. Okay, so we'll do this example. 7 B's, 1A, what is it? 1A, 7 B's, 1A, 7 B's. 1, 2, 3, 4, 5, 6, 7. And then 3 A's, 1, 2, 3. Okay, so now the thing that's complicated about this problem, right, which seems complicated, is like, what happens if like these A's aren't touching, right? So that's not like Alice can't remove this A because they're not touching each other. But what if Bob ends up removing all of these B's? And then these two A's will be touching, so then there'll be an additional valid move. So the thing that makes this problem seem complicated is like, well, I can go through one time and I can quickly calculate all the B's and A's that I can remove, right? If I'm looking at all the A's I can remove and all the B's I can remove, right? And I go through this, I can say, can Alice remove this A? No, you can't even move anything on the edge, so that's fine. Can Bob remove this? No, well, Bob can't remove this. Can Alice remove this B? No, Alice can't remove a B. Can Bob remove this B? Well, no, because one neighbor is A. Can Bob remove this B? Well, yeah, there's one neighbor that's a B and another neighbor that's a B. So, yes, no. Can Bob remove this B? Yes, because so that's another one he can remove. I'm just counting through. These are all going to be B's, obviously. 3, 4, 5. And then here, can Bob remove this B? Well, one neighbor is a B and neighbor is an A. No, so no, 5. Can Alice remove this A? No, because one neighbor is an A, B. Can Bob remove it? No, he can't remove A's. Can Alice remove this A? Yeah, one neighbor is an A, the other neighbor is an A, so yes. Can Bob remove this B, this A? Well, no, Bob can't remove B's. No, and no. So in this totally, there's 5 B's, right? When you do one pass, Bob is 5 and Alice is 1. So obviously Bob's going to win, right? And even if you could combine these, he still won't win. But just to prove a point here, what I'm trying to say is, like, well, what happens when Bob removes all of these? What if Bob removes all of these? Now, isn't there going to be an Alice here, right? And then this Alice moves over? So would that create another A? Like, could I eventually remove this A? Right, that's the thing that makes this problem seem like it's complicated, because you can do one pass easily, right? We do one pass easily. We just look at 3 adjacent elements. We say, okay, can Alice remove this? Yeah. Can Bob remove this? Yeah. So on and so forth. But at what point does it like, what if things get adjacent that weren't adjacent before, and that causes a new element that can be removed, right? What if Bob makes a move that causes Alice to be in a position where now she can remove an additional piece, right? What if this situation changes? Well, it doesn't change, right? It's impossible for the number of moves that can be made to change from the initial number of moves that can be made. When you make that initial calculation, that is the total number of moves that can be made. And there's really nothing that can make that no longer the case. And why is that? Well, think about it, right? Let's just walk through this example of Bob removing all the B's, right? When Bob removes all the B's, right, we'll start 7 B's. 1, 2, 3, 4, 5, 6, 7, 1, 2. Okay, well, Bob removes a B, so let's say he removes this B. So it becomes A, B, B, B. I'm going to leave it like this so you can see. It's going to be a lot of drawing here. All right, A, B. Now this B can go. Maybe you already see this, and this is a waste of time, but I think it's just constructive when you have additional time to remove. Now, of course, you might be looking at this and saying, like, how the heck are you removing this? Well, I'm just not pushing them back together, right? But this B is now adjacent to this B, right? This B is now adjacent to this B. B, A, right? So what I'm doing right now, if it's not clear, is I'm trying to remove all the B's to see if we get an additional set of A's. Because right now, my calculations, initially, there's only one A and there's 5 B's that can be removed, right? Does that change based on what Bob does or based on what Alice does? And my argument is that it doesn't, right? So, and why is that? Now we're in this situation. Bob has removed 5 B's, just like our initial calculation. And can Alice remove now more A's? Well, no, she can only still remove this A because these B's, given the way that the problem is set up, the way I thought about it, they're like walls, right? Because you can only remove a B that's between other B's. So no matter how many B's you remove, those 2 B's on the edges will always persist, right? You can't remove the B's on the edges, right? The B's on the edges can never be removed. So what does that mean in terms of the contribution to the problem? Well, since these B's can never be moved, the initial question here was that these A's would touch each other. These A's can never touch each other because those B's at the pillars, at the edges, they're like walls that can't be passed. Hopefully that makes a little bit of sense, right? So all that really signifies about the problem is that, well, this initial calculation is the final calculation, right? Regardless of what happens, because you can remove all of these B's, but you can never remove these edges. So these A's will never touch each other, right? So even though we're removing things and we're pushing things together, since it always has to be things that are within 2 of the same letter, those 2 letters will just get shrunken down all the way till this point, right? And I'll rewrite it without the spaces, right? And these 2 B's are now trapped together, right? You're just condensing them, but it's never gonna like evaporate, right? It's never gonna disappear. So you take these B's and you push them all the way in, but there's still only 2 B's, so these A's are no longer, they're not gonna connect and touch. The number is never gonna change. The initial calculation is the same as the final, okay? So we're gonna do the A idea as 0 and the B idea as 0. All right, now remember at the end we said Alice can only win if she's strictly greater than B, right? Because she goes first, so she has to have more than Bob in order to win. Because if they both have 1, Alice removes 1, Bob removes 1, now Alice has 0. And Bob has 0, but Alice's turn is next, so she loses. So A has to be strictly greater than B. All right, and then what we'll do is we'll just go through all the colors, right? Now, we don't have to consider the edges, right? Because there's nothing to the left of 0, the first element, right? Nobody can remove the first and last element, regardless if it's A or B, because there's no neighbor to the left of 0, and there's no neighbor to the right of the final element, right? So we'll do length of colors minus 1. That way we're looking at all the elements from 1 to the end, but not the first element, not the last element. And then we'll just do a check and say, well, if colors of I minus 1 equals colors of I equals colors of I plus 1, so if these 3 adjacent elements are equal, well, if colors of I equals A, right, because we're saying if these ones are equal, well, if they're all equal and they equal A, well, then that means it's something that A can delete. Else they're all equal and it's not A, so the only other thing it could be is B, so B plus equal 1. Now, this is the initial calculation, right? This is me walking through this thing manually and saying, okay, A, B, like counting through and accumulating the value as I go through by looking at each 3 adjacent, right? Because really what I did here is I just looked at 3 adjacent, 3 adjacent, 3 adjacent, 3 adjacent, right? And since we kind of consider the fact that when you smush things together, you never get rid of the walls, right? Even if you have like 100 elements in a row that are all the same color, when you push them all together, there'll just be 2 remaining, and those can't be passed. So it's not going to change. It's not going to change adjacencies, right? If there's a B, an A, and a B, no matter how many A's are in between those 2 B's, they're never going to be able to touch each other to make another valid calculation. Apologies. So with that, let's go ahead and run, and then let's submit. All right. So what is the run and space complexity of this? All right, well, let's say that n is the length of colors as it was given. All right. Well, for time, what do? We look at all n elements, n minus 2, n. We say, are these three adjacent elements equal? So it's 3 calculations. Then we do one thing, one thing. So this is all constant operations, n times. So we do n constant operations. We do a constant check at the end. So that's just O of n time. All right, what about space? Well, we create these 2 variables. We use the array that already exists, so we don't create anything. And we just update these 2 variables. So that's constant space. All right, guys, have a beautiful rest of your day. It's been a long time since I made a video. A lot of my life has changed, personally, professionally. Maybe I'll make a video on that. I don't know. But yeah, it's been great solving this problem with you guys today. Later.